Hello everyone. Today's topic is about equilibrium concentration of electron and hole. Equilibrium, that means by thermal equilibrium. As you know, thermal equilibrium means there is no external excitation except temperature. That is excitation, that is the electron from the valence band transition to the conduction band by overlapping forbidden energy gap. That process is called excitation. It is the excitation process through the energy which is consumed by the electron in the valence band. So the energy that is consumed by the electron mainly by three ways, either by optical source or called as light, or by voltage, or by temperature. These are the three ways. Along these three ways, except temperature, other two, that is by means of voltage and by means of light, there should not be any excitation occurs. That is the first condition of thermal equilibrium, that is given as no external excitation except temperature, and net movement or net motion of current or charge equal to zero. That is, if there is a positive current, there should be a negative current, that is equal in magnitude but opposite in direction, so the net current is equal to zero. So it is at thermal equilibrium, the concentration of electron and hole are represented as N0 and P0. Okay, N0 represent electron concentration, P0 represent hole concentration. N0, here we have to derive totally 8 expressions, on which the first expressions of N0 and P0 is listed out by the integration form. It is found out with the help of energy band diagram. In the energy band diagram, I want to take a energy range called dE, which is already listed out in the figure. In the dE, I am taking a unit volume, that is 1 centimeter cube volume, which is given as a shaded portion in the conduction band diagram. In this unit volume, the number of states called as density of state, that is N of E. N of E, that is density of states, which is number of states per unit volume. So N of E, if we know the N of E, that is the density of state, we can say the maximum number of electrons or holes that can occupy in the region. If we know the density of state, if we know the probability of finding electron, that is F of E, then we can find the electron concentration, that is N0 is equal to integral EC to infinity F of E N of E dE, because F of E N of E represent electron concentration per unit volume. F of E N of E into dE represent the electron concentration in the range dE. Electron concentration in the range dE. Now the total electron concentration in the conduction band is given as integral EC to infinity F of E N of E dE, where the limit is ranging from EC to infinity, because EC is the bottom energy level of conduction band, infinity represent the highermost energy level of conduction band. Similarly, the hole concentration is represented as integral minus infinity to EV, because minus infinity is the bottom energy level of valence band and EV represent the top energy level of valence band, into N of E 1 minus F of E dE, because N of E, that we know the density of state, 1 minus F of E represent the probability of finding holes. So if we multiply the density of state with the probability of finding hole, we can get the hole concentration per unit volume. If we multiplied it with the factor dE, we will get the hole concentration in the energy range dE. If we perform the integration with the limit minus infinity to EV, we are getting the total hole concentration in the valence band. And you have to know the Fermi-Dirac distribution function F of E, that is proportional to 1 by E, that is inversely proportional to the energy level. And so all these explanations were already given about N of E, F of E, dEV, and N of E 1 minus F of E, N of E 1 minus F of E dE. Okay. Now the second state of expression. For that, I am considering the total number of states. the total number of state in the conduction band as Nc and the total number of state in the valence band as Nv. F of Ec, as we know, the probability of finding electron in the conduction band. F of Ev, the probability of finding electron in the valence band. 1 minus F of Ev, probability of finding hole in the valence band. Okay, now we can find the N0, P0 without the integration because the total number is listed. So N0 equal to NCF of EC, and we can see NV P0 is equal to NV1 minus F of EV. As we know, the expression of F of E, that is 1 by 1 plus e to the power E minus EF by KT, which is already explained on the previous class. We can find F of EC, that is 1 by 1 plus e to the power EC minus EF by KT, which is substituted in the equation. And as you know, EC is greater than EF, so EC minus EF is very much greater than KT. Thereby, e raised to EC minus EF by KT, which is the exponential factor, that is very much greater than 1. So 1 plus e to the power EC minus EF by KT. In that factor, the factor is neglected. So the denominator is taken to the numerator side by taking the ratio as negative power, and we can have the N0 is equal to NC e to the power minus of EC minus EF by KT. Similarly, by substituting F of EV equation using Fermi-Dirac distribution formula, and by crossing multiplying the factor for the getting of common LCM, and by assuming the fact that EV minus EF, that is very much less than KT, thereby e raised to EV minus EF by KT very much less than 1, we can have P0 is equal to NV e to the power EV minus EF by KT. Okay. Now about intrinsic semiconductor. In an intrinsic semiconductor, you know EF is equal to EI. Okay, where EF is equal to EI means the intrinsic energy level and the Fermi level are equal, which is already shown in the energy band diagram. And as you know, in the mass action law, the electron concentration and hole concentration are same, that is N0 equal to P0 equal to Ni. So substituting these two factors in the previous equation, you will get N0 as Ni equal to Nc e to the power minus of Ec minus, instead of EF substitute it as Ei by KT. Now similarly for the expression of P0, we are getting P0 equal to Ni equal to Nv e to the power Ev minus Ei by KT. Substituting these two new values of N0 and P0 in the mass action law N0 P0 equal to Ni square, you will be getting Nc Nv e to the power minus of Ec minus Ev by KT. The energy difference between conduction band and valence band is nothing but forbidden energy gap, Eg. That is why the Ni square is equal to Nc Nv e raised to minus Eg by 2 KT. And from the equation 1 and 2, we can rewrite what is Nc and Nv by taking out the factor to the left hand side. So Nc is equal to Ni e to the power minus e to the power Ec minus Ei by KT, and Nv is equal to Ni e to the power minus of Ev minus Ei by KT. Substituting these two now values of Nc and Nv on the equations N0 and on the equations of N0 and P0, we will be getting N0 is equal to Ni e to the power Ef minus Ei by KT, because in the equation we can see Ec and minus Ec are cancelled, only the factors of Ei and Ef will be remained inside the exponential power. Similarly, P0 is finally getting as Ni e to the power minus of Ef minus Ei by KT. So here we are again finding the new expression of electron and hole concentration in terms of Ni. Okay, so totally 4 set and totally 8 expressions we have to study about the electron concentration and hole concentration. That's it. Thank you.